Hello everyone, welcome back to the course on measurement in instrumentation, and today is the fourth lecture of this 10th week where we are discussing about signal conditioning, and today we will continue our discussion on analog to digital converter. In the previous class we have seen voltage to time AD converters and we called it ramp type because we were using a ramp generator there. Okay. Now let's tweak it little bit and let's discuss today another AD converter which is based on voltage to frequency conversion. Okay, and let's call it voltage to frequency AD converter. Sometime we also call it integrating type AD converter. Okay, as the name suggests, the input voltage controls the frequency of an output pulse train, and say if V in is the analog input in the system or in the ADC and F out is the output pulse frequency, in that case for the voltage to frequency AD converter, F out is directly proportional to the input voltage applied. Okay, and exactly it works on the same principle that when you have input voltage or say this output frequency of certain pulse, okay, is controlled by this input voltage. Okay, this is a typical voltage to frequency converter. Okay, voltage to frequency AD converter. Okay, if you see, it has a integrator, a comparator, a pulse generator and a counter to give the digital out. Now let us see its working in little brief. Okay, an analog input, say V in, is applied to the integrator. So you have the input voltage over here to the integrator. Okay, the integrator converts the input voltage into a ramp signal whose slope is proportional to the input voltage signal level. Okay, or if you see the output from this integrator, where R is this input resistance and C is the feedback capacitance, let me call it feedback capacitance. Okay, and this is your input resistance. In this case, the output of this integrator, which is of course a function of time, will be equal to minus 1 by RC integration of V in over certain time. Let me call it say any value from t1 to t2, or let it be simple integration of dt. So V naught or V naught t is equal to minus 1 by RC integration of V in into dt. Okay, now here this V naught is the output voltage of the integrator, V in the input voltage that we have seen, and R and C are the input resistor and feedback capacitor. Okay, now dV naught by dt I can write from this equation. I am not considering the sign here. Okay, dV naught by dt is equal to V in by RC. Okay, or if you see, we can say that this is the slope. Okay, this is the slope. Now slope is directly proportional to the input applied voltage or input analog signal. Okay, that's why I mentioned that the integrator converts this input voltage into a ramp signal. Okay, and this ramp signal slope is proportional to the input voltage signal level. Okay, now since you are also using a sample and hold circuit, okay, means that you are keeping this V in constant even for a temporary time, or we have seen that a sample to hold circuit actually freezes the input voltage for a very small time period, maybe of the order of say picosecond or microsecond. Okay, and during that I can say that V in is constant, although please note that in practical purposes V in is continuously changing. Okay, however, since we are sampling it, okay, or we are doing this digital conversion, V in we are considering it as a constant during this conversion. Okay, now at that point V naught is, we have seen that minus 1 by RC integration of V in dt, or I can write V naught equal to minus V in by RC into t. Okay, now let me again not consider this sign conversion right now. We'll take it later wherever required, but the slope I can write as V in by RC. This is what we were discussing. Okay, now comparator detects the ramp and compares with a preset threshold level. Let me call this preset threshold level as Vt. okay, and when V naught is equal to Vt, it generates a trigger pulse. Okay. So, it keep on comparing it with a threshold level Vt, and once this output matches with this threshold level Vt, okay, it generates a trigger pulse. Okay. Now, from the ramp equation, we have seen that V naught is equal to V in by Rc into T. Okay. Now, at the trigger point, V naught will be equal to Vt. Okay. And I can write that, let me call this equation, say equation 1, okay, or Vt, and we have seen, say, let me call this equation 2, okay. We have seen from equation 2 that V naught is equal to Vt, okay. At this particular point, Vt will be equal to V in by Rc into T, okay. Let me call this equation 3. Okay. Now, if I rearrange this equation 3 and try to find this time t, okay, this time t will be equal to Rc into Vt by Vin. Okay. This is the time required for ramp to reach the threshold voltage, and please note that once it reaches, there is a trigger pulse generated. Okay. Now, apart from detecting the ramp and comparing with the preset threshold level Vt, a current pulse is also produced which discharges the capacitor of the integrator, after which a new ramp is initiated. Okay. The time between successive threshold level crossing is inversely proportional to the slope of the ramp. Okay. The slope of the ramp is V in by Rc, that we have seen. We have called it slope V in by Rc, okay, and T is equal to Rc Vt by V in, all right. So, if I write it, say, let me call it slope S is equal to V in by Rc, okay. We have seen this from this equation that slope is equal to V in by Rc, okay. I can write Rc by V in as 1 by S or 1 by slope, or if you see, T is equal to 1 by S into Vt. And that is why I have mentioned that the time between successive threshold level crossing is inversely proportional to the slope of the ramp. Okay. Since the slope of the ramp is proportional to the input analog voltage, from this equation we have seen that V naught is equal to V in by Rc into T. Hence, the frequency of the output pulse from the comparator is directly proportional to the input voltage. Okay. So, frequency of the output pulse, say f, is directly proportional to the input voltage, and this is exactly with which we have started this discussion on voltage to frequency AD converter. We have seen that the output frequency is governed by the input voltage. Okay. Now, say we have seen that T is equal to Rc into Vt by V in, or frequency can be written as 1 by T or can be written as V in by Rc by Rc into Vt, or I can say that this F out mathematically is equal to V in by Rc into Vt. Okay. Now, the output frequency may be measured with the help of a digital frequency counter. We have seen in the illustration that I have a counter which is giving the digital output. Okay. So, the output frequency can be measured with the help of a digital frequency counter and can be encoded to whatever signal level you wish. Okay. So, advantage of this voltage to frequency AD converters are like it has a very high noise immunity. Okay. They have good accuracy for even slow signals. It has also a simple digital interface, because if you see, I have digital counter at the end and getting the digital output directly. Okay. A long distance signal transmission is possible because you are having now a frequency signal, okay, which can be transmitted over larger distance. Okay. However, they are again having several disadvantages, like the conversion speed of this AD converter is also slow, and this require accurate timing circuits. Okay. Because if you have seen that what I have done here is I am using a integrator and a comparator and a pulse generator. Okay. So, The timing is very, very important because your frequency is dependent on that. Okay. So it requires accurate timing circuits, and if there is any error in the timing circuit, there will be error in the output. Okay. It is limited for high frequency input signals and usually avoided for low frequency signals. Okay. Then we have another AD converter that is known as dual slope integration AD converters. Okay. This dual slope integration AD converters are very, very crucial, particularly when you want your signals to be protected from noise, or wherever noise cancellation, particularly from power signals and other nearby signals are required. Okay. The dual slope integrating ADC is very accurate analog to digital converter that converts an analog voltage into digital number using two integration phases. Okay. So two integration phases are, first, integration of the input voltage, and the second stage is de-integration using a reference voltage. Okay. Although one step is integration and another step is de-integration, we call it two integration phases. Okay. Now, because it involves this two integration process, okay, it is also known as dual slope ADC. In fact, there are two different slopes also involved. We will see in our discussion. Okay. This converter is widely used in digital voltmeters or DVMs because it has excellent noise rejection and it also has high accuracy. Okay. A dual slope integration AD converter is shown over here. You can see that it also uses a integrator. Okay. This is the integrator that you have also seen in the previous discussion. Okay. I have a switch, okay, which can toggle between a negative reference voltage and a positive input voltage. Okay. Let me call it, say, minus V reference. Okay. And I have a positive input voltage, say V in. Okay. There is a comparator and a control logic, and clock is fed into the control logic. Okay. It is generating two signal, say reset and count, and then I have a digital output here. Okay. So this is a typical dual slope integration AD converter. Okay. The reference voltage, say minus V reference, okay, and the input analog voltage, we called it V in, okay, are sequentially connected to the integrator with the help of switch. Okay. So as I have mentioned that this switch can move from this to this point, say let me call it, say, point 1. Okay. Let me call it, say, point 1, and say this is point 2. Okay. This is 1 and this is 2. This switch can move from this point to this point, but please note that at one time either the input voltage is connected or the reference voltage is connected. Both cannot be connected at the same time. Okay. So the reference voltage and the input analog voltage are sequentially connected to the integrator with the help of the switch. Okay. The reference voltage and the input analog voltage, please note that, has to be of opposite polarity. Okay. So if V in is, say, since it is continuously moving or continuously changing, okay, say if I have this kind of input signal, okay, the reference voltage, say, in this zone and in this zone can be like this. Okay. The reference voltage and the input analog voltage must be of the opposite polarity, and this is important, and this is the heart of the dual slope integration AD converter. We will see that how this negative reference voltage helps in getting two different slopes. Okay. The input voltage is integrated for a fixed input sample time. Say input voltage is V in and this is applied to the integrator, and let the integration occurs for a fixed time, say for T1 time. Okay. So I have an integrator, for example, let me not make it complicated and make it, say I have an integrator, okay, and this switch is connected to the V in, okay, and this integration or this connection of switch is kept for, say, time T1. Okay. Now, this phase of integration is also known as run-up phase in case of this kind of AD converters, and at this particular moment V naught, which is a function of t, will be equal to minus 1 by RC integration of V in over dt. Okay. Now, since V in is constant temporarily, we have seen that in the previous discussion also, because sample and hold circuit will keep it freezed for certain time. Okay, V naught will be equal to minus V in by RC into T1. Okay, so the integrator output becomes a negative ramp. Okay, now at the end of integration, if Vp is the peak ramp voltage, so say if it is going like this, for example, okay, or say I have something like this. Okay. Now, if Vp is the peak ramp voltage, say this is Vp, Vp will be equal to minus this Vp. Now, V naught I am replacing it with Vp, and this Vp will be equal to minus V in by RC into T1 at the end of this time period. Okay. The integrated value is then discharged at a fixed rate, and the time to do this is measured by a counter. Okay. Two type of commands are given by the logic control to the counter, and these two commands are a reset command and a convert command. Okay. Reset command we understand, but let's see what is the convert command. Okay. When a convert command is received by the counter, it automatically resets to all zeros and then switch connects the input voltage to the integrator. Okay. Now, the output from the comparator is designed such that at this time it will permit the counter to count up for a output from the integrator will be steadily increasing in value. Okay. And the next count will cause it to go all zeros and start over again, and at this point the switch actually changes its position. Okay. Now, the input voltage is disconnected and the switch connects the reference voltage to the integrator. Okay. This we have seen from the schematic that the switch will move from input voltage to the point 2, which is the negative reference voltage point. Okay. Now, at this particular point, the positive input voltage is cut off from the integrator. Now, this process is known as deintegration and also called as rundown phase. Okay. Therefore, the integrator now integrates the opposite polarity voltage, the minus V reference, which causes the output to move towards the 0 voltage. Okay. Now, say this opposite polarity voltage, which is known as reference voltage, is V reference, or we are calling it minus V ref, because this has to be shown as a negative voltage as compared to the input voltage. Now, V naught t at this point will be equal to minus 1 by RC into V in, and V in here is minus V reference into dt. Okay. Now, say if T2 is the rundown time, okay, then V naught can be written as V reference by RC into T, and T can be replaced with T2. Okay. So, V naught is equal to V reference by RC into T, and I am replacing this T with T2, which is the rundown time. Okay. Now, to return from the Vp value to 0 value, V in RC into T1, we have to equate it with V reference by RC into T2. Okay. Let me cancel this RC from both the side, and V reference T2 is equal to V in into T1. At this point, just rearranging things, I have T2 equal to V in by V reference into T1. Let me call it equation 5. Okay. Now, the rundown time in terms of this run up time and this V reference can be given as T2 equal to V in by V reference into T1. Okay. Please note that during this duration, the counter is counting up from 0 again. Okay. When the output of the integrator goes to 0, it causes the comparator to switch its output, thereby stopping the counting via the control logic. Okay. The binary number in the counter at this time is proportional to the amount of time that it took the integrator to integrate down from its starting point to 0 value. Okay. Therefore, the binary count is proportional to the input voltage. Now, figure here shows the output from the integrator during the conversion cycle. Okay. This is the time T1 I was mentioning, and this is the time T2. Okay. T2 is the time where the counting is up to the reference voltage and T1 counts up to the input voltage. Okay. The difference in the slope of the curve, like I am talking about this slope and this particular slope, okay, of the curve is due to difference in the voltage level of the input voltage V in and the reference voltage V reference. Okay. Now, suppose T1 is the count when the input voltage is applied and T2 is the count when the reference voltage is applied. The input voltage V in is equal to T2 by T1 into V reference, and this we have also seen from our previous discussion. Okay. Now, the during rundown time T2, the clock pulse is counting, okay, or clock pulses are counted. So, if clock frequency is say f clock, the digital value n is equal to f clock into T2. Okay. Now, substituting this T2 from our previous discussion, we have found that T2 is equal to V in by V reference into T1. Okay. Now, substituting this from our equation 5 into this value, I have n equal to f clock into V in by V reference into T1. Now, rearranging these values, okay, I have n equal to T1 f clock by V reference into V in. Okay. Now, let me take this T1 f clock and V reference together as a constant, okay, k. In that case, k n is equal to k into V in, okay, or I can say that n is proportional to the input voltage. Okay. So, the digital count is actually proportional to the input voltage, and we have seen that how the analog to digital conversion is happening. Okay. There are several advantages of this particular kind of AD converters, like they have very high accuracy. Okay. They have excellent noise rejection. This excellent noise rejection is coming from this equation. I have V in equal to T2 by T1 into V reference. Okay. Now, you can also write this in terms of frequency. Okay. And once you write it, okay, you will see that since I am using a ratio in place of the absolute time or frequency values, they try to cancel it out, okay, and noise rejection becomes even better. Okay. These kind of AD converters are insensitive to component variations, and they are good for low frequency signals. Okay. We have seen that from the previous discussion that the voltage to frequency AD converters were good for high frequency signals or high frequency input signals, but this dual slope based devices or dual slope based AD converters are also good for low frequency signals. However, the conversion speed is something that you have to sacrifice, okay, and they are not suitable for high speed systems. Okay. For high speed systems, we have other kind of advanced AD converters like sigma delta ADCs and others that we have named it in our previous class. Okay. Like if you talk about a sigma delta converter ADC, it converts an analog signal into digital form using different components or different methodologies or different stages. Okay. It has oversampling stage, integration, and then doing the noise shaping. Okay. Now, this is not a one-step conversion from voltage directly to the or input voltage directly into the output digital signal. Okay. Now, it is in place of that, it produces a high frequency bit stream which is then filtered and decimated to obtain the final digital outputs. Okay. However, the further discussion of this advanced ADCs are beyond the scope of this course. We just started this ADC discussion just to understand the signal conditioning system of our measurement system. Okay. I hope that we have now achieved certain knowledge of conversion of analog to digital signals as well as from digital to analog signals. Okay. We will be using it maybe later on in our next module, but before that there is one important concept that I wanted to discuss, that is grounding and shielding of our measurement instrumentation, and in our next class we will be discussing grounding and shielding in little brief. Thank you.